The overall goal of this experiment is to show the effect of reactor length and width, volumetric flow rate, and use of barriers on reaction conversion in microfluidic reactors. This will confirm predictions made from Peclet and Reynolds number calculations. This is accomplished by designing the reactors in SOLIDWORKS using knowledge of the principles of mixing. The second step of the procedure is to simulate the reactor in COMSOL software to observe fluid flow patterns and calculate predicted conversions. The third step of the procedure is to print the reactors using preform software on Formlabs 3D printers. The final step of the procedure is to run the reactants through the reactors, then titrate the effluents to calculate experimental conversion. Ultimately, results can be obtained that show the patterns of fluid flow and calculate reaction conversions through the use of software simulation and additive manufactured device testing. Generally, individuals new to this method will struggle because the principles of mixing must be understood by the user. This is done in order to develop an effective reactor design and increase reaction conversion. On the other hand, simulating the reactor design in COMSOL and confirming these results using 3D printing makes reactor design approachable to a range of scientific disciplines. Begin designing your reactor by opening the SOLIDWORKS software. Select the top plane for your first sketch. Sketch a square with lengths of 50 millimeters. Extrude this sketch by 4 millimeters to form the base of the reactor. Next, select the top surface and sketch your reactor design. Use a Smart Dimension tool to specify distances and relations. Keep the channel design at least 5 millimeters away from the edges. Extrude cut this sketch by 2 millimeters. This will be your reactor channel. Create a plane on top of your channel. Sketch a square directly over your base. Extrude this sketch by 2 millimeters to form the top of the reactor. Next, select a side of the reactor where you would like to insert a port for fluid flow. Sketch circles that are 4 millimeters in diameter. They should be 3 millimeters from the top and at least 6 millimeters from the sides. Extrude these sketches by 6 millimeters. Create new sketches on top of these extrusions. Draw 2 millimeter diameter concentric inner circles. Extrude cut these sketches by at least 11 millimeters. This will form the 4 ports for the reactor, 2 inlets at the beginning, 1 quench near the end, and 1 outlet at the end. Make sure to check the locations of each cut by using the section view to ensure that all ports are in the desired locations. Finally, save the file as a stereolithography file or .stl to be used for printing. To create the COMSOL-ready file in SOLIDWORKS, first copy the channel sketch into a new part file. Extrude this sketch by 2 millimeters. Finally, save the file as a .stl file. Next, open COMSOL Multiphysics. Using the Model Wizard, create a 3D model with laminar flow and transport of diluted species. Finally, use a stationary study. Change the length units to millimeters and import the file you just created. For this simulation, you will want to use liquid water as your material and set an incompressible flow. Select the inlets and outlets, define the reaction species and equations, and specify the inflows and outflows. For these reactors, the triangular mesh with size for normal fluid dynamics is recommended, but depending on the complexity of the reactor, a finer mesh may be necessary. Now, compute the study. Plots can be generated and surface averages can be calculated from the results. A parametric sweep can also be generated here. To set up the print, open the preform software. Select the layer thickness, material, and version number based on the resin used for printing. Then apply these settings. Import the reactor.stl file. Change the orientation so that the ports do not touch the bottom of the print surface and the reactor is at least 20 degrees above the horizontal. Generate supports for the reactor. Remove any supports that are on the face of the ports, as these could be difficult to remove without damaging the reactor. Change the layout so the reactor prints in the desired quadrant. Before starting the print, check the tank by using a comb to remove any residual solid resin from the previous print and add additional resin so that the level falls between the minimum and maximum resin lines. Now, the reactor design can be sent to the printer. Confirm the print by pressing the front button to the display screen on the printer. The average print time is around 3 to 4 hours, but can vary depending on the complexity of the reactor design. When the print finishes, open the printer and remove the platform. Apply isopropanol around the base of the scaffolding attached to the platform. Carefully use a scraper to remove the print. Place the print in an isopropanol bath and wait at least 10 minutes to dissolve the uncured resin. Apply deionized water to the outside and inside of the channels to remove any excess isopropanol. Remove the scaffolding with pliers. Be careful not to deform the reactor or ports, as this will affect the results and ability to attach tubing. Before testing, setup of the reactor and titration station is necessary. Begin by preparing stock solutions of 0.1 molar isopropyl acetate, 0.1 molar hydrochloric acid, and 0.1 molar sodium hydroxide for the reaction, as well as 0.01 molar sodium hydroxide for the titration. Fill 3 syringes with 50 milliliters of each of the reaction stock solutions. Secure the syringes to the syringe pump. Attach tubing to each of the ports on the reactor. Attach the opposite ends of the tubing to the corresponding syringes. Secure the reactor to a ring stand with a clamp. Make sure to level the reactor so that gravity does not alter the flow rate through the reactor. Place a waste container at the end of the outlet tubing and run the syringe pump at 5 milliliters per minute until there is a steady flow at the outlet and there are no air bubbles in the reactor. Prepare a small graduated cylinder in a larger beaker packed with ice for sample collection. Replace the waste container with the flask and set the desired volumetric flow rate on the syringe pump. To set up the titration, secure a burette to a ring stand, close the end of the burette, and fill with the titration stock solution. Now the reactor can be tested. Simultaneously begin pumping solution through the reactor and begin timing. During collection, constantly swirl the flask to make sure the reaction is completely quenched. Once 10 milliliters have been collected, simultaneously stop pumping and timing. Record this time. Replace the flask with the waste container to collect any drops. Remove the graduated cylinder from the ice beaker and pour the product solution into an Erlenmeyer flask. Add 1 drop of phenolphthalein to the product solution and swirl to mix. Begin titrating with sodium hydroxide while constantly swirling the flask. Stop titration when the solution stays pink in color for more than 30 seconds. Record the volume of titrant used. The reaction used in this experiment was the saponification of isopropyl acetate and sodium hydroxide to produce sodium acetate and isopropyl alcohol. Modifying reactor design and flow rate can cause the extent of this reaction to change. In order to predict the difference in conversion for each independent variable, the Peclet and Reynolds numbers must be calculated using the equations seen here. Microfluidic reactors with high Peclet numbers have minimal diffusion and systems with low Reynolds numbers have slow mixing. Therefore, reactors with lower Peclet numbers and higher Reynolds numbers are expected to have better mixing and greater extent of reaction. COMSOL simulation plots and surface averages can also be used to predict the extent of reaction based on fluid flow. In physical testing, after titrating each product solution sample, the percent conversion for the reaction can be calculated. This is found by dividing the number of moles of hydroxide ions consumed, which is equal to the number of moles used to titrate the solution, by the number of moles of hydroxide ions that were fed in. In this experiment, we looked at the effect of channel length and width, use of barriers, and volumetric flow rate on reaction conversion in microfluidic reactors. We first looked at 3 different channel lengths. Based on the same Peclet and Reynolds number calculations, as well as similar COMSOL concentration profiles, we expected similar outlet concentrations for all lengths. Based on our trials, we confirmed that reactor length does not have a significant effect on reaction conversion. Next, we looked at 2 different channel widths. Based on an increased Reynolds number as well as differing COMSOL concentration profiles, we expected the thinner channel to have greater product outlet concentrations. Based on our trials, we confirmed that thinner reactor width does increase reaction conversion. Then, we modified the reactor to include boundaries in the flow. Based on an increased Reynolds number as well as differing COMSOL concentration profiles, we expected the channel with barriers to have a greater product outlet concentrations. Based on our trials, we confirmed that adding barriers within the channel does increase reaction conversion. Finally, we ran the reactants through the reactor at different flow rates. Although decreasing the flow rate results in a decrease in both Peclet and Reynolds numbers, the change in Peclet number should have a greater effect. However, these numerical differences are not observed within the COMSOL concentration profiles. We expected a slower flow rate to have a greater product outlet concentrations. Based on our trials, we confirmed that slower flow rates increase reaction conversion. Therefore, we recommend decreasing the width of the channels, adding barriers, and decreasing the volumetric flow rate to improve reaction conversion. After watching this video, you should have a good understanding of how mixing is affected by reactor design and microfluidic devices.